Hello friends and welcome, and this video is going to be the next video on Perceptron. In this video we are going to build a multi-layer Perceptron. In our previous video you have seen a single layer Perceptron. We just take a training data and just analyze that training data and learn with the training data and then predict the output. Now we are going to do the same with this multi-layer Perceptron only, but the difference is that in multi-layer Perceptron we add an extra layer in our Perceptron model called hidden layer. So we have three layers. First is input layer, second is hidden layer, and third is the output layer. And we have two weights. First is the weight connecting the input layer and the hidden layer, and the second weight is the which is connecting hidden layer and the output layer. So let's directly jump to our code. Let me create a folder name MLP. So our whole code is going to be in Python. Let's write our interpreter line. So this whole code is going to be nearly of 40 lines, and we do not need more than 40 lines. In our library we are going to use NumPy. We are going to define our activation function. So in this we are going to use the same activation function, sigmoid. It takes one input and return sigmoid with that function. And now next is a sigmoid derivative. So we have defined our two function. Now we are going to define our neural network class. Define its constructor and the input. Self dot inputs is equals to inputs. Now self dot L is equals to length of the input. Now self dot Li is equals to length of, let's write it as self dot input. So input is a multi-dimensional array. L contain the value of the whole array, and the Li contain the length of the second array. Now we will define our weights. First the weight which is connecting the input layer and the hidden layer. Now the second weight. Self dot L. So we have defined our both the weights. The first weight Wi is of 2 by 4 order. Not order, its length and the number of rows in the column, and the hidden weight are of 4 by 1. Now let's define our method which is going to predict the result. So S1, because now we have two layer, so we have to write one more line of code. I just forgot to write np before. Now it's time for s2 sigmoid np.dot. Now the output of the first layer will act as an input for the second layer. So now we are going to return the output of the second layer, that is the overall output of the neural network. Now it's time to train our neural network. So we are going to write our train function, and it take the input, outputs, and the number of iteration only. So for I in range it, L0 is input, L1 is equal to sigmoid np.dot. Same procedure again which we have done in our think function. Now it's L2 sigmoid np.dot. So here dot means the dot product of both. It should not be L0, it's L1 WH. So it's L2 error equals to outputs minus L2. Now we have to find out L2 delta is equals to np.multiply L1 error, not L1, it's L2 error. And there is also one spelling mistake, it's now correct. L2 error in the sigmoid derivative of L2, one extra bracket. Now like this we are going to do for the hidden layer also. L1 error np.dot L2 delta hidden layer weight. So now it's time for L1 delta is equal to np.multiply multiply L1 error into sigmoid derivative of L1. So now it's time to update the weight. np dot L1 dot t L2 delta self dot w wi is equal to np dot L0 dot t L1 delta. So our training function is complete. Now let's run this program with some input test data. Then I am going to explain you this program. Inputs to np dot array 0, 1, 1, 0, 1, 1. So now after seeing input you can see how you can easily find the value of ln and l1. So l is going to be value 4 because 1, 2, 3, 4, and l1 is going to be 2 because it has 2 values only. It's time for output. np array 0 1 1 0. Our output is also complete. N is equals to neuron, not neuron, it's nn. Just forgot the function class name. np dot train inputs, outputs, and the number of time you want to train it. Now let's do one thing. Print the weight. I think I do not need to print the weight again. In previous video you can see how weight changes. Now let's do one thing. Print the test result before and after the training. Let's add a space here. After training. So copy this from here to here and change after to before. So before training. Now save our program and open a terminal and see if there is any error. Provided permission to execute. So you can see we have error. We haven't provided the input to the class. You can see we also have error here s2 on line number 21 in function think. s2, it's not s2, it's s1. Now we have run something. We have error in training on line number 37, spelling mistake 37. Let's correct this spelling mistake. DELTA. Now let's run it again. Now it's running successfully. You can see we have result before the training which are 0.7, 0.8. Now we have result 0.01, 0.98, 0.98, 0.9. So which are nearly, we can say 0.110 as our output. If we just give it more and more training, like I have increased my iteration from 10,000 to 50,000, we can just reduce error many folds. Now you can see we have 0.00, 0.99, 0.99 and 0.00, which are nearly 0.110. So we have trained our model on the XOR gate. You can take another gate like NAND gate and train it for NAND gate, and it will give you correct output. So that's our code which is running successfully. I think I just need to add one thing also, a random dot seed. I just forgot to seed it. Import IMP and import random. Run it again. So random.seed, I have added it, and you want to know why. It's a good practice to seed your random number. You will still be getting random distributed, but they will be randomly distributed exactly the same way each time you train. So this means that every time you iterate you will get the same random number. Just see, we are getting the same random number every time. If I just print the weights, then I will get the same random again. So The main thing in neural network which helps to helps the this perceptron model to learn is the backpropagation algorithm. It's the main algorithm, and it helps in improving our model. To so to improve our model, we first have to quantify just how wrong our predictions are. Then we just adjust the weight accordingly so that the margins of error are decreased. Like in forward propagation, backward propagation calculation occur in each layer and occur in two steps. So first is we find the margin of error of the output result to back out the necessary changes in the output sum. So first step is we have done is here you can see we have the output which is with the correct value, and this L2 is the predicted value. So we have find out the error. Now the second step, we extract the changes in the weight by multiplying output sum by the hidden layer result. So here is the second step. We have just find out the how much change we have to made in our weight, and we have used this L2 delta here to update the weights. So the derivative of the sigmoid, we have used activation functions sigmoid, and the derivative of the sigmoid give us the rate of change. Since the output sum margin of error is the difference in the result, we can multiply that with the rate of change. So this gives us the delta, and we can use that to update the weight. So to update the weight, we just multiply the input value with the delta value. You can see here we have just the input value which we have transposed, and we have the delta value. So to update the weight, we find their dot product, or you can simply multiply, because as you know. So we update the weight here, and the number of iterations we do, the more improved answer we get, the more our model learn. So this is the overall of the multilayer perceptron for the XOR gate. I hope you liked the video and you enjoyed it a lot, and if you enjoyed it, then hit the thumb up button, the like button, and subscribe to my channel for more videos. And if you still have any query left in your mind, then comment below and I will answer all your queries. Thank you. Have a nice day.